So section 2.1, we're starting off with functions. So this is the first mapping that we have here. So a function is just a rule that assigns an input variable from one set. So that's at A. And it's going to map it to one and only one element in another set B, and that's going to be our output. We're also going to talk about function notation, which we'll use for the rest of the course. And f of x, so this f and then the x in parentheses, it's red f of x, and it means a function of x, and it's the same thing as y. So we're not going to use the y notation all the time. Sometimes we will, but function notation is a lot more powerful, and I'll show you why in a minute. But first, let's just look graphically at what is a function and what is not. So this first one is not a function because this input value 3, it's getting mapped to two different output values. And for it to be a function, it can be mapped to one and only one output value. The second case is a function. I have 1, 2, and 3 are my input values. They're all being mapped to 4, but that's fine as long as they're not mapped to more than one thing. So this part is a function. So why function notation? Well, we're going to be talking about applications, business applications. And it allows us to differentiate between different functions. So if I wrote all of these as y equals 3x minus 100 and y equals 4x and y equals x plus 100, then I'd have to figure out, well, which function really is telling me what. But if I use this notation p of x, which we're going to use, which is a profit, r of x for the revenue function, and c of x for the cost function, then it's very clear which function that we're talking about. So if I say, well, find the revenue if we sell 100 units, I'm going to be looking at this function, and I'm just going to plug in 100, and I say, well, if I sell 100 units, the revenue is going to be $400. It's also useful when we're evaluating a function. So if I have f of x is 2x squared minus 1 and g of x is 5 minus 10x, and we want to evaluate the function f of x when x is equal to 1. So I'm looking at this function, and everywhere I see an x, we're just plugging in a 1. So we get 2 times 1 squared minus 1 plus 1. And when you evaluate that, it just comes out to be 2. So instead of writing a whole sentence, this tells me which function to use, and this tells me what to evaluate it at. So g of 7, now we're in the g function, so 5 minus 10 times 7, so we have that written out here, and simplify that, we get a negative 65. We're not going to just be evaluating these at actual real numbers, but we'll also be evaluating it with other variables, and we're going to be composing functions. So here for part C, we have f of a. Again, I'm back to this f function, and anywhere I see an x, now we're going to substitute an a for that. So we get 2a squared minus a plus 1. Looks like the same function. All it did really was change the variable. And then for this part D, I have g of a plus h. So here's my g function. So 5 minus 10, instead of the x, we put a parenthesis and we put a plus h. And then the last step was just to distribute that, and we get 5 minus 10a minus 10h. There's no like term, so I can't do anything more than that. All right, our next thing is composition of functions. And when we compose functions, it's sort of like what we were just talking about in this upper section. It's just instead of just plugging in a number or a variable or a combination of variables, you're going to take one function and plug it into the other function. So there's two different notations. This little circle, which people say fog, I don't know, it drives me crazy, but f of g of x. I like this notation better because it just tells me what I'm plugging in. So the outer function here is f, and then I'm plugging in the g of x function into the x function. So we're still using the equations from above, and we want to find f of g of 2. So I can either plug in the g function first, or I can plug in the g of 2 first and then plug it into the f. So that's how I typed it out here for you. So g function was 5 minus 10x. And so for that x, we're plugging in 2. So we get 5 minus 10 times 2, or 5 minus 20, and that's a negative 15. And then I'm going to go to the f function and plug in negative 15. So it was 2x squared. So that's where that first was. And we're plugging in negative 15 minus x. So minus a negative 15 plus 1. And then simplify that. So that simplifies to 466. And we're going to come back and do some more composition of functions at the end of this unit that are a little bit more complex. But this is just an introduction to it. All right, so back to the mappings. The mappings are the input values and the output, which I talked about. The input values we refer to as the domain, and those are the x values, the independent variable. And the range are the y values, or the dependent variable. And we're going to have to define what these domain and ranges are for different functions. Right now we're going to look at it algebraically, and then we're also going to look at it graphically in another section. So I want to find the domain, and I need to find, again, the domain is all possible x values. Now if I just have an equation, it's harder to find the range. So when we look for range, we're going to do it more when we have the graph than when we just have the equation, unless it's something that we know like really easily that we can tell. So the first one, I have the square root of x minus 1 is my function, and I know we are not allowed to have a negative inside the radical. So therefore, I need to know when x minus 1 is greater than or equal to 0. Because I can take the square root of 0, but I can't take the square root of a negative number and get a real number. So x minus 1 has to be greater than or equal to 0. We solve that by just adding 1 to both sides. So my solution, my domain, is x is greater than or equal to 1. Or, in the interval notation, the 1 is included, so we have a bracket by it, and then it goes to infinity. For part B, I have 1 over x squared minus 4. We know we're not allowed to have division by 0. So I need to know what makes that denominator 0. I know that x squared minus 4 is not allowed to equal 0. So we're going to find out when it is equal to 0. So factor that. It's the difference of two perfect squares. So x minus 2 times x plus 2. And then set each factor equal to 0. So we get 2 and negative 2. And these are the factors that x is not allowed to be. Because if I plugged in 2 or negative 2 into this, I would have 1 over 0. So I can either write my domain as just x cannot equal 2 or negative 2. Or, again, in interval notation, I have it written out. It can go from negative infinity to negative 2. Then I have to skip over it. So that's why there's parentheses. And then negative 2 to 2. And then skip over 2. And then go from 2 to infinity. So all of those have to be parentheses. Now part C, we have just a polynomial. G of x is x cubed minus 8x plus 5. I can plug in anything I want for x and evaluate it. So my domain for this is all real numbers. And again, in interval notation, it's from negative infinity to infinity. So these are super important. If I'm being asked to find the domain, there's only two things I have to worry about. One is I cannot have division by 0. And the other is I cannot have imaginary solutions. So no negative values inside of square roots. If it's a polynomial, the domain is just all real numbers. But these are the things that you want to have in mind when you're looking to find the domain.